Okay, let's continue. If you recall, we left off here where we proved that the entropy is an extensive function of its independent variables, namely the total internal energy, volume and number of particles. So, we have called this the fundamental relation of thermodynamics. So, what I want to do now is to see if I can go ahead and calculate this entropy function for specific examples. So, specifically I am talking about the entropy of ideal quantum gases. So, just to point out that the if you recall, we had studied in quite significant detail the problem of marbles on a staircase. So, specifically I have in mind an infinite staircase. So, imagine that there are n number of identical marbles on an infinite staircase. So, I have already told you that identical particles is a characteristic feature of quantum mechanics. So, specifically in the case of marbles, I have also suggested that there is no restriction on how many marbles can be placed on a single step. So, this is an example of what are called bosonic particles. So, in quantum mechanics, so when there is no restriction on how many particles can occupy a certain energy levels, that is called, those particles are known as bosons. And they are also non-interacting particles in the sense that the energy of a certain level is an intrinsic property of that step. It is not related to how many bosons are sitting on that step. So, this would not be the case, for example, if the bosons or the marbles had some kind of energy by virtue of the fact that there are other marbles next to it. So, if that were the case, then the energy of the marbles on the step would not be proportional to the number of marbles on the step. So, we are going to disregard this aspect and we are going to assume that if there is one marble per, so in other words the energy of a step is just proportional to the number of marbles, and the proportionality constant is independent of how many marbles there are. So, this example would be called ideal Bose gas, an ideal collection of bosons specifically. So, suppose you wanted to describe fermions, ideal fermions, what you have to do is, instead of saying that I do not restrict the number of bosons on each step, you say that there is a severe restriction, namely there is a maximum of one particle allowed per step. So, in other words, a step can accommodate either no particles at all or exactly one particle and no more. So, in such a case the system that you would be describing is called an ideal Fermi gas. Okay, so now let me recall that we had started off, we had reached this point where we had tried to evaluate the entropy using the saddle point method. So, we had reached this stage where we said that the entropy function is nothing but the saddle point value of this function WQ. So, what I want to do in this lecture is I want to explicitly evaluate this for an ideal Bose gas and for an ideal Fermi gas. So, I want to explicitly evaluate the entropy function for an ideal Bose gas and an ideal Fermi gas. So, let us see how to do that. So, the way you do that is that you start with this definition of W, and then you just try and see if you can first solve for the values of phi star and theta star, and recall that those values are the ones that make the W an extremum. So, in other words, it is the saddle point itself. So, theta star comma phi star is precisely the saddle point, and the value of WQ at the saddle point is proportional to the entropy function. So, now if you go ahead and evaluate this, and remember that you have to set this equal to 0 in order to be describing the saddle point, and then what you do is that you will be able to convince yourself that the total internal energy and total number of particles are going to be of this form. So, now recall that we had defined the function that whose saddle point we have to find as WQ, and the entropy function was nothing but the number of particles times this WQ at the saddle point. Now, in order to find the saddle point, what you have to do is take this function and find the extremum. In other words, the first derivative with respect to this parameter called theta has to be set to 0, and the first derivative of this parameter W again with respect to this with this functions sorry, this is phi should be set to 0. So, when you do that, you see is that you will be able to derive a formula for this. So, you can eliminate well, rather you can express u and n. So, notice that think of this as your unknowns, and there are two unknowns and two equations, and this f was derived earlier. So, if you recall, f was way back here, and this was my f here, and so it is a function of theta and phi. So, I am going to take the logarithm of that, and if I take the logarithm of so the log of f q is going to become q times summation over j times log of 1 plus q times e raised to minus I theta epsilon j times e raised to minus I phi. So, that is what log of f q is going to be, and I am going to use that directly here. So, I am going to assume that I have used that here. So, if I do that and if I think of u and n as my unknowns, and recall that u is nothing but the energy density. So, energy per particle. So, I have defined small u as energy per particle. So, this is my small u. So, I can finally read off just by thinking of small u as my unknown and big N as my unknown. So, effectively u and n as my unknowns, and I have two unknowns and two equations, and when I solve it, I end up getting this using the value of f that I had written down earlier. So, I strongly recommend that you follow along with a notebook and pen and pause this video and try to fill in the gaps yourself, because it is quite tedious for me to explain all the steps. So, not only am I interested in knowing a formula for u and n, but notice that I have determined u and n implicitly in terms of the saddle point, namely theta star and phi star. So, now I am going to see if I can relate some of these saddle points to other parameters that I am more comfortable with, such as temperature and chemical potential. So, given the fact that the entropy function is nothing but total number of particles times this function W at the saddle point. Now, the reciprocal of the temperature, as you very well know in thermodynamics, is the slope of the entropy function as when plotted as a function of internal energy. So, when you do this, you will be forced to evaluate such a derivative, and when you do that and you evaluate it at the saddle point, and also you use this identity here. So, it's a few steps are involved. So, you should bear with me. So, I am just substituting the value of W n there, and what I am going to do is, so this is basically my log of f q, if you recall, and there was a q there. So, this q times log of f q is what that is. So, I am forced to differentiate whatever is in this bracket with respect to u, and you see that everything depends on u, even the saddle point depends on u. So, I should not forget to differentiate the saddle point with respect to u, and there is a u also outside the saddle point right there, which of course I have to differentiate. And when I do all that, I end up with this. And now I go ahead and I just recognize this, remember that this is nothing but it is basically the with that epsilon j inside, that is nothing but the total energy u, and what is this? If I pull this outside, whatever remains is total number of particles. So, now, so you see as a result this cancels out with this cancels out with this, and I end up with this answer. The theta saddle point is simply related to the absolute temperature of the system. So, in a similar way you can convince yourself by using this identity or this definition rather of the chemical potential that the phi saddle point is very easily related to the chemical potential and of course temperature. So, so as a result now I do not have to write everything in terms of my saddle point, which is a very mysterious object. So, instead of thinking of theta star and phi star, which we will be hard pressed to attribute any physical meaning to unless we perform this calculation. Now that we have performed this calculation, we know that the saddle point is directly related to the absolute temperature and the chemical potential. So, I am going to go ahead and make use of this and write e raised to I theta as 1 by T. And by the way, I am measuring in this course, as I perhaps told you, that I will be measuring temperature in energy units. So, as a result, the Boltzmann constant is taken to be 1. So, in which case 1 by T is inverse of temperature, and there is a notation for this, a standard notation in thermodynamics, and that is called beta. So, I am going to use this notation and rewrite these two expressions here in terms of beta and mu. So, you see I am going to be able to do this. So, and Q is the numerical constant that determines whether I am talking about bosons and or fermions. So, if Q is 1, I am talking about fermions, and Q is minus 1, I am talking about bosons. So, where did this creep in? You should think about why suddenly a Q creeped in. In fact, it did not creep in, it was there all along. So, I will just remind you where it kind of started coming in. It came all the way here when I was trying to. So, if I decided to sum over all the particles up to infinity, that means there is no restriction on the number of particles, then I am going to get a 1 over 1 minus some quantity here. So, however, if I had decided that there was a restriction that it is only up to 0 to 1, then it will be in the numerator it would become 1 plus this quantity. So, in other words, if Q is plus 1, it corresponds to fermions. If Q is minus 1, it corresponds to bosons. So, that is where that comes from, that Q. So, now you see, recall that the entropy function, strictly speaking, is a function of in thermodynamics it is a function of the total internal energy, volume and number of particles. So, however, in this example we have been writing the entropy function in terms of the saddle point, and of course, we have shown that the saddle point is nothing but chemical potential and temperature. So, what we should do, in other words, is we should be able to invert these two relations, and notice that here the left hand side are total internal energy and number of particles, and the right hand side involves chemical potential and temperature. So, what we should do is invert these two relations and rewrite temperature and chemical potential in terms of total internal energy and number of particles. So, if you do that, then you can go ahead and substitute those expressions into your saddle point, which is of course temperature, chemical potential, and then you will be successful in expressing the entropy in terms of its bona fide or genuine independent variables, namely total internal energy and number of particles. So, coming back to this point, that so we can rewrite, we can think of this u of the total internal energy as the sum over all the energy levels. Whatever I am summing is the energy level itself times a function called n of j. So, I can think of this u and n as being this sort of sum, where this n of j now has the physical interpretation of the average number of bosons or fermions in that energy level. So, it has the interpretation of the average number of bosons or fermion, because that is clear from this, that if you sum over all the energy levels, you get the total number of particles, and if you first multiply the energy of each level times the average number of quantum particles in that level, and then you sum over all the levels, of course, you are going to get the total internal energy. So, this is called Fermi-Dirac distribution if q is plus 1, and it is called the Bose-Einstein distribution if q is minus 1. So, we have been successful in deriving both the this is very important, because you will see that in many StatMech books they spend a lot of effort deriving this, and but we have done it quite easily. So, I should impress upon you that the derivation that I have presented in this series of lectures is somewhat novel, that you will not find it easily anywhere else. Okay, so now I am going to also point out that, of course, the main quantity of interest was actually entropy all along. So, remember I told you that is really the fundamental thermodynamic quantity of interest. So, now entropy function is simply related to this the function w, whose saddle point we have decided to focus on. So, now having found the saddle point, we just go ahead and substitute the values of the saddle points. I told you that they are related to temperature and chemical potential, and then you put them back in and you get an expression of this sort. So, this is my formula for the entropy function, and of course, you have to keep in mind that the independent variables are supposed to be only u and n, but it appears that here it still involves beta, which is inverse temperature, it still involves mu, which is chemical potential. So, I also told you that there is a way to get rid of beta and mu and rewrite it in terms of u and n, and all you have to do is just invert these two relations here and here. So, now we can go ahead and derive something called the equation of state. The equation of state is nothing but a relation between pressure, volume and temperature and number of particles of a gas typically. So, well, in this case I will not be dealing with volume until a little later, because I am still discussing marbles on a staircase. So, there is the notion of volume still does not have any concrete meaning here until I actually commit myself to be describing a gas, then only volume comes into the picture. So, I will do that a little later, but now just use your thermodynamic identities and use your fundamental relation of thermodynamics, and then you compare these two. We just derived this result, and this is nothing but the fundamental relation of thermodynamics, and you simply compare the two and you get what is called the equation of state. Okay, so, this is the equation of state. So, of whatever gas you want. So, if q is plus 1, you are talking about the equation of state of ideal Fermi gas, and if q is minus 1, you are talking about the equation of state of an ideal Bose gas. Alright, so now I also want to go ahead and explicitly evaluate some of these. So, I want to do the summation specifically. So, for a gas. So, I do not care about marbles anymore. So, up till now this summation was over energy levels, and the example was through a staircase with marbles. I still care about marbles, of course, they are bosons, but I do not care about the staircase anymore. So, I am going to instead think of this as the energy levels of free particle confined to a box, perhaps of a volume L by L by L. So, you have a box which is a cubical box with sides L. Alright, in that case, so recall that I am discussing quantum particles. So, if I have quantum particles, I have also told you the ideal. So, ideal quantum particles means they do not interact with each other. So, they are independent particles. So, it is sufficient to solve a one body problem, which you know from Griffiths how to do for a single quantum particle trapped in a box of cubical box of side L, and the wave functions are nothing but this. So, this is the wave function, or rather this is the wave function, and it is going to be described by these three quantum numbers nx, ny and nz, and these quantum numbers are forced to be 1, 2, 3 etc., and so on. because 0 is excluded, because if any one of them is 0, the wave function itself becomes 0, and then it violates normalization. You want the normal the total probability to be 1, and if the wave function itself is 0, the total probability can never be 1. And finally, n cannot none of these n's can be negative, because if the wave function is flip sign, it's basically is like multiplying by an overall phase, and you know that two wave functions that differ by an overall phase corresponds to basically the same state. So now I am going to rewrite so the energy of this wave function is really the energy of the free particle, which is p squared by 2m, and p is nothing but h bar times the magnitude of the wave vector, which is k, and the wave vector itself has three components, kx, ky, kz, and kx can be written in terms of this quantum number nx, and similarly ky and kz. So now the sum over the index j has to be now reinterpreted as the sum over the three quantum numbers nx, ny, and nz. Also, I am going to finally rewrite this quantity beta times epsilon j, which appears all over the place. Well, it appears everywhere. I am going to use this idea to rewrite this in a more manageable way later on. So, recall that I can rewrite epsilon j in this fashion. So, when I substitute that here, it is going to look like this. So, keep in mind that I want to study what is called the thermodynamic limit. So, I have a bunch of quantum particles that are trapped in a box, a cubical box of side L, but then I do not want my box to really have boundaries in the end, that I want it to be a uniform quantum gas. So, how do I achieve that is to not have boundaries, or first have boundaries and make the boundaries go so far away that any finite region of the box can be thought of as being spatially uniform. So, that is the idea of thermodynamic limit. So, what we are going to do is we are going to assume that the box is huge and the number of particles scales with the volume of the box. So, that the density of particles, that is number of particles per unit volume, remains fixed. So, that is called the thermodynamic limit, and we are going to work in the thermodynamic limit. So, now it so happens that in the thermodynamic limit, these summations, which are really annoying because they are very hard to do, can actually be converted to integrations, which are easier to do. So, you do not have to do discrete sums in the thermodynamic limit because you can always convert them to integrations. So, in order to do that, I am going to prove the following theorem. So, you will have to bear with me because again it seems rather technical, but it is very important for you to follow along, because I have noticed that especially this crucial idea that in the thermodynamic limit you can replace a discrete sum by an integration is rarely explained in any of the books. So, typically you first encounter it in you should encounter it typically for the first time in a statistical mechanics course, but you also encounter it in solid state physics course, and none of those books I feel do proper justice to this idea. So, it is worthwhile to spend some time trying to prove this rigorously, so that we will be fully convinced about its validity. So, in order to do this, consider an even function of this integer n. So, imagine that there is an integer n and this is an even function. Well, of course, 0 is not really needed. So, an even function is one where you flip the argument, you get back the same thing. And now I am going to think of lambda times n, because I am going to think of this lambda as a small quantity, and that is because you see the n squared always comes with an L squared associated with it, but in the denominator. So, in the thermodynamic limit, what will happen is that my lambda is really proportional to 1 by L, where as L tends to infinity in the thermodynamic limit, lambda is a small quantity. So, that is the whole idea of thinking about a function of a lambda times an n. So, now imagine that I perform this summation. So, I am going to define a quantity called j of lambda, where j of lambda is nothing but this sum as defined. So, recall that I should exclude the n equal to 0, because then the wave function itself becomes 0. So, I start from 1 all the way up to infinity. Now, I am going to ask myself, is there a way I can avoid doing this summation, or can I somehow replace this with something more manageable? So, the answer is yes. It so happens that you can prove, or we are going to prove it right now, that when lambda tends to 0, this summation, rather this discrete sum, can be replaced by this integration. So, it is quite remarkable, and this is a rigorous result that we can prove right now. Well, we are going to prove it subsequently. So, but let us use it right now instead of well, we will postpone the proof for a little while later, but I am going to use this now. So, remember that in the equation of state, I am forced to sum over all the j's, and then sum over all the j's is nothing but summing over the n's. Now, so as a result, in the equation of state, I will be forced to do this. So, so I put the v. So, remember there was a v there, and v is nothing but L cubed, and I have written L cubed as when it comes to this side, to the right side, becomes 1 by L cubed, and I have written 1 by L cubed as 1 by L times 1 by L times 1 by L. So, now I have this kind of a combination 1 by L times summation. So, now I am going to rewrite this beta times epsilon j, which is all over the place, as lambda times n squared plus lambda times n y squared times lambda plus lambda times n z squared. So, then I am going, where lambda is of course this, we can just read it off because we know what this is, and from there we can read off this lambda, and then I am going to define this C naught in this fashion. So, as a result, this is nothing but C naught by twice L. So, now if I multiply both sides by C naught cubed, right. So, C naught is nothing but, so from here we can see that C naught is nothing but 2 L times lambda, or basically L times 2 lambda. So, what I am going to do is if I multiply by C naught into C naught into C naught, which is C naught cube, and C naught is L times 2 lambda, and L cancels with 1 by L. So, I end up with 2 lambda, 2 lambda, 2 lambda. So, now remember that lambda times summation over n from 1 to infinity, we just proved that that is this quantity j. So, lambda times summation from 1 to infinity is nothing but 1/2 of the integration, right, with respect to this whole thing called capital X. So, now we relabel lambda of n x as capital X, lambda of n y as capital Y, and lambda of n z as capital Z. So, it is like integrating over capital X, capital Y, capital Z, and remember that there was a 1/2 there, and there are 3 1/2s, and then there are 2 times 2 times 2, and all that cancels out, and you end up with this result. So, basically this is nothing but the volume integral of over this dimensionless vector whose components are capital X, capital Y, and capital Z. So, as a result, I will be successful in rewriting the equation of state in this rather nice dimensionless form. You will have to excuse my misuse of notation here. Earlier I had used small u to be a number of total energy per particle. Now I have defined it as total energy per volume. So, maybe I should put a subscript there, small u subscript v, implying that it is the total energy per unit volume, that is the energy density, and the number of particles per unit volume is nothing but capital N by V. And just as we were able to rewrite the equation of state in terms of this dimensionless integration over the dimensionless vector. So, all the summation over j have now in the thermodynamic limit been replaced by this integration over r, which is a dimensionless vector. So, we have expressions for the energy density number of particles and the equation of state, all in terms of simple dimensionless quantities. And we can now go ahead and use this in our fundamental relation, and we will be able to rewrite the entropy in terms of, so suppose I am successful in performing this integration, which is likely to be far easier than doing a discrete sum over integers, and not just one integer, but 3 different integers, and that is likely to be far more difficult than this. So, notice that here we can make use of spherical symmetry, and even though technically there are 3 components, but then there are no angles in the integrand, and we can make explicit use of that. We are going to make explicit use of that later on. Alright, so now using that, we can go ahead and substitute these intensive quantities. Remember that these are intensive quantities in the sense that if I scale the number of particles by lambda, scale the volume by lambda, because these two are extensive, I end up getting a rho which is independent of lambda. So, as a result, all these small case alphabets, Latin and Greek, they are intensive quantities, and the uppercase alphabets are extensive quantities. So, the entropy function is therefore the extensive volume times a whole bunch of intensive quantities, where you have so this is the fundamental relation of thermodynamics, and I am going to just plug in these p's, u's and rho's. Okay, so then I get this entropy function. So, if Q is 1, I am describing fermions, non-interacting fermions, and Q is minus 1, I am describing non-interacting bosons. Okay. Now, let us come to the technical part. So, even though this seems a little technical, it is really nice to know this proof once and for all. So, remember that I am trying to prove that this j, which is nothing but lambda times sum over f of lambda n. So, that is what j is. So, if I take lambda tends to 0, this summation is, I will be able to replace it by the integration. So, how do you prove this? It seems rather hard to prove, except that if you realize that any function f can always be written in terms of simpler functions. So, this can be as complicated as you want, but however, you can always, according to Fourier, the mathematician Fourier, you can always write any function f of x in terms of really simple functions e raised to I k x. So, what is the beauty of this really simple function e raised to I k x is that as a function of x, it is a very simple function, because it's infinitely many times differentiable, it does not blow up anywhere, it has no singularities, you can do whatever you want to do it, pretty much whatever you do to it, it remains as it is. It is like neutrino, it just passes through. So, you can differentiate it once, well, an e raised to I k x, apart from a innocent prefactor like I k, it remains the same function. So, you can integrate it again, you get back the same function. So, that is the beauty of the exponential of x. So, it remains, you can do calculus very easily with it. So, now it is very comforting to know that any complicated function that does not have those properties can still be rewritten, not just of course as one of these, but as a whole bunch of these. So, you will have to multiply this by an appropriate prefactor, and then you have to add up a whole bunch of them. So, adding in this context means integrating over that parameter k, because you will be forced to take into account all the different k's there if you want to mimic a general function f of x. Now, it so happens that well, this is completely devoid of any meaning unless I am also able to tell you a prescription for how to get g of k. So, the idea is that you can get g of k if somebody tells you what f of x is, then you can go ahead and perform this integral. So, this is the content of Fourier's theorem, which says that these two put together are mathematically consistent. So, that is another way of saying, so if you take this expression, you put this here, because you change x to x dash and you substitute here, you should get an identity, and if you, the reverse is also true, you take this, put that there, you are going to get an identity. So, I am not going to do all that because Fourier analysis is not part of this course. So, I am going to assume you already know this, and if you do not, please learn it yourself by reading the appropriate maths books. So, now I am going to use this. So, remember that this is what I have to find the sum of. Now, I am going to rewrite this f in terms of its Fourier coefficients. So, I am going to write this as a Fourier transform. So, now I am going to sum over all the n's, and when I do, I get this, this is a simple geometric series. Notice that this is nothing but something raised to n. Well, that something happens to be e raised to I k lambda. So, now when I sum over all the n's, well, not all the n's, from n equal to 1 to capital M, but finally, remember that I have to, the infinite sum is formally defined like this, where you sum from 1 to a certain value m, and then you take the limit as m tends to infinity. So, remember that I have committed myself to an even function. So, that also makes the Fourier components even, that you can easily convince yourself of. So, now I am going to have to take this limit as m tends to infinity, and so there is m sitting right there. So, the idea is that if you take lambda really small, this is going to be bounded between 1 and minus 1. But however, it is this quantity. So, I have rewritten that here, and I have multiplied and divided. So, I have put this outside there, and I have multiplied and divided by this quantity. And so, now this is the singular thing that I have to worry about. So, when m tends to infinity, that if k is not 0, this thing oscillates and becomes 0, but if k is 0, so this thing only survives when k is 0. So, when k is not 0, it becomes 0. So, when k is 0, this cost becomes 1. So, I have been a little blasé here and kind of ignored this altogether. I strictly should not have done that, but it's kind of there, it's lurking out here. But the point is that if I stare at this ratio, then I convince myself that this is nothing but the Dirac delta function, and because of that, this cost becomes 1, and then this becomes 1/2 of g of 0, and then I get back this result. And g of 0 is nothing but, what is g of 0? G of 0 is, if I put k dash equals 0, I get this becomes 1. So, g of 0 is nothing but the integral of f. So, it is 1/2 of g of 0, and I get this result. Okay. So, as a result, so this is the proof of this theorem. Of course, it is not going to be fully convincing to a mathematics audience, because I have been rather sloppy in places, but you get the idea that you can fill in the gaps yourself. Perhaps you can make it more rigorous if you wish, but this is the general sketch of the proof. Okay, so now now I am in a position to derive the Maxwell-Boltzmann distribution of a ideal classical gas. The reason is because we have taken a lot of trouble in deriving the Fermi-Dirac and Bose-Einstein distributions. Let's go to that, and so remember that this is what that is. So, if q was plus 1, I am talking about the Fermi-Dirac distribution, and q is minus 1, I am talking about the Bose-Einstein distribution. So, the idea is that can I make use of this derivation that I have spent so much effort in deriving, which is applicable to a quantum gas, and see if I can take the some appropriate limit and get a classical expression for its classical counterpart. And the reason why you can do that is because you all know that classical mechanics is can be just thought of as a appropriate limiting case of quantum mechanics. So, how do you obtain classical physics from quantum physics? You can think of Planck's constant as a variable and send it to 0. So, that is one way of thinking of obtaining classical physics from quantum physics, and alternatively you can imagine the mass of a particle as variable and send it to infinity. And lastly, you can think of the temperature of the system as variable and send it to infinity, even then you will be describing classical system even though you started off with a quantum system. So, I will end here for this hour and I will get back to doing this, namely I want to be able to derive the Maxwell-Boltzmann distribution of a classical gas using the Fermi-Dirac and Bose-Einstein distribution that we have so painstakingly derived. All right, thank you and hope to see you for the next hour.